All right, welcome all of you. This is Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and today we are here to solve some problem based in the topic one and two dimensional NMR spectroscopy for the chemist. Yeah, and we are almost nearly we have already covered almost half of our course, and uh, so we'll solve the some problems based on the topic multiplicity pattern and the nomenclature of the coupled spin. So here there are I would like to just show some few slides regarding the just uh, a kind of uh, review, which here we have given the coupling constant between the cis and trans as well as the geminal and vicinal protons here. Particularly, uh, you need to keep this value. Remember, this is kind of axial hydrogen, right? And this is equatorial hydrogen. So and the coupling constant between these two protons is nearly zero point 0.6 hertz here. Similarly, if we have the uh, same axial and equatorial hydrogen in the five-member ring system, so here the the coupling constant JHH coupling will be the 5.5 hertz. And if you have some systems like this one, which has the two hydrogen attached to the carbon, which attached to the nitrogen, it's like imine two hydrogens of these imine. So which couple strongly couple show the coupling constant about 16.5 hertz, and in the aldehyde, which is again very high, 42.2 hertz. So this is some example. This question generally, uh, if someone preparing for competitive exam, then they can refer this value. So most of time the question came directly. You just need to uh, give the value. This is just for information purpose. And also, if you have the uh, alkanes, and we need to give the order of the exact coupling constant value. So here we have the hydrogen and equatorial hydrogen here. So we call it as a staggered conformation, right? And for this one, the angle here is 60 degree. So here, the coupling constant between the both hydrogen will be the 2 to 5 hertz. Similarly, for this type of hydrogen, so for the anti-conformation, which is 10 to 16 hertz. And if you have the again the conversion, which is like same as the initial one, 2 to 5 hertz. So this trans anti-conformation has the highest coupling constant in this type of systems. The next question is sorry, next one point is in case of cyclohexane system, we have the axial equatorial couplings, and this coupling constant, which is nearly 2 to 4.5 hertz. Similarly, if you have the equatorial hydrogens, which has the coupling constant 2 to 4.5 hertz, and we have the both axial protons, then it will be the higher 8 to 11 hertz. And generally, most organic chemistry deals with the aromatic compounds, and we have the orthocoupling, metacoupling, and paracoupling of this proton. Here mentioned, if you have the two hydrogens which are ortho to each other, the coupling constant is higher, so which is about 6 to 10 hertz. Generally, in most of it case, it is like 8 hertz nearly. If you have the meta coupling, then it is like 2 to 1 to 3 hertz. Generally 2 hertz or 3 hertz in a practical example. If you see, then it will you may found in the NMR spectra. It has the coupling constant about 2 to 3 hertz. Similarly, we have the para hydrogens. At that time, the coupling is generally not observed. And if we have some very high precise instrument, That time we may found some couplings here, which might be 0 to 1.5, or even most of cases it doesn't absorb the para coupling in the aromatic compounds here. So before going to the questions, do you have any doubt regarding the topics which are covered in the 6 week? We can solve some problem based on that one then. Uh, any doubt regarding the questions in the assignment? All right, if you don't have doubt, then we'll directly move to the problems and we'll solve some similar problem based in the assignment. So I will not give the exact answer, but I will just direct you to go up to the answer. So the first question in the assignment is like a methyl group, a CH3 group we have given, is coupled with the three chemically inequivalent CH. So this CH3 group is coupled with CH, CH, and CH. Let's take like this one, two, and three. These three uh, CH groups are there, and given the coupling constants are given. So the coupling constant for this one is the 12 hertz. For the second CH is 8 hertz, and for third CH is given the 20 hertz, right? So I will just give the numbering A in the form of ABC, right? And the C. So we have to give the chemical shift of this proton are well dispersed and separated by 1 ppm. All right. So what will be the multiplicity pattern seen in the seen for the methyl group? So we have to give the multiplicity pattern for this methyl group, right? And which coupled with the I will just come in 1 minute. Sorry, there was some issue was there. So all right. So we have to give, we have given here, we have to give the multiplicity of this one. And if you look at the options, they have given the options like it will show the triplet of triplet of doublet. The second option here given, all right, we will not draw all the options, but the options are given in this manner. So if you look at the, uh, if you try to solve this one, so if you first we have to give the splitting for this one, right? So let's take this methyl group, which coupled with the proton here. Uh, when we draw this such diagram, we have to take the we have to see the first coupling, which the coupling with the maximum J value, right? So let's take this J value is 20 hertz, right? So this one, because of this CH3C, CH, it is this C, right? Then because of the another, the CHA, because of this CHA also show the doublet, right? This will be the 12 hertz, right here. Then we have the another CHB, right? So because of this CHB, again we will get the doublet. It has the 8 hertz splitting. Sorry. Similarly for this one also, uh, this doublet will be like this, right? Because it is 8 hertz, it will be slightly smaller. Again, this one here, 8 hertz. for the same here also 88 hertz this J value. So if you look at the what the splitting in this one, so we have the doublet of doublet, right? In this manner. So we get here the answer for this one, doublet of doublet of doublet. So in this manner, we will get answer here for this four doublet, right? Am I right or wrong here? Only three. So we just take the first, sorry, here. For this doublet, we get, for this first coupling, we get the doublet. And for another coupling, we get here the doublet and doublet. For because of all these three, we get the doublet, the pattern like in the manner of doublet of doublet of doublet. The next one is the chemical structure of the cis and trans stilbene are given. So we have given this cis stilbene and the trans stilbene. And the question is, can it distinguish by the ONH NMR scalar coupling alone? By using only the J values, are you able to get the, are you able to get the, can you distinguish these two? So if we look at the this one, it has the uh, symmetry, right? And these two protons are equivalent. In the similar manner, these two protons are also equivalent. So if you look at these two protons, they will not couple with each other. So we get only the singlet because of these two. And for this one also, we get the singlet in the 1HNMR. So there is no, we will not observe any J value here. So if you look, give the labeling A and B. So this HA is equal to HB. So we'll not observe any kind of coupling in this one. So this question is in this question we are not able to distinguish by the this scalar coupling alone. But if you look at this these two example, in this one we have given the malic acid and fumaric acid. They are like geometrical isomers of each other, right? And we have this cis, and this is the trans. So can malic acid and formic acid, whose structures are given below, distinguished by the ONH NMR using the chemical shifts of protons, right? So if you look at here in this one, so the cis and trans in this one, so the delta value for these protons, let's give for these protons, both are protons are equivalent here. I will label as a AA, and these protons are as a HB and HB because both are symmetrical. So delta value for the HA is not equal to HB. So that's why we are able to distinguish this malic acid and fumaric acid by using the
Sir,
1H
I have a
NMR
doubt.
sector. Yes.
The same case should have been for cis-stilbene and trans-stilbene, right?
Uh, uh, Here we are comparing the delta values. So delta values are different for these protons. But
Okay, okay.
if you look at the initially, the question is here mentioned, can they are distinguished by the uh, I'll just highlight this couplings only by using only the J values or the coupling constant value, whatever the value is. Are you able to distinguish the cis and trans? But if you look at these two compounds, so in these two compound, uh, they will not couple with each other because they are identical, right? So we have seen the identical protons they will not couple with each other. So we get here only one signal due to this both hydrogens. So we get only one signal here. So how we can distinguish by using only the coupling constant value? But if you look at this here trans stilbene, here also the same we will get the one signal. But if we look at the NMR spectra and we have the mixture, so we get the for signal for this cis-stilbene and the trans-stilbene at two different value. It will not the delta value for I will give this label as a and this also A, this as a B, this as a B. The delta value HA will not be equal to the delta value of HB. So which is more deshielded here? Does anyone have any idea in this one? If you just Google the delta values for the olefin protons of the cis-stilbene and trans-stilbene, the delta values for these protons are different here. So that's why we can able to distinguish by the NMR, but not only using the coupling constant value, because they are not at all coupling, right? So we get only one signal in the both compounds. So by there is no I mean we will not observe any kind of splitting for these protons. But in this one, we have given the in the third question here, they mentioned like, are you distinguished by using 1H NMR using the chemical shifts of the protons? Yes, we can able to distinguish by using chemical shifts. So the cis protons and the trans protons of this malic acid and the fumaric acid, so they have the different delta values. So we can able to distinguish by using the delta values. Got the answer here?
Yes, sir.
Next different type of question. These two question I thought it will be a tricky. That's why I just solve this one. But if you look at the remaining questions, I don't think there should be any issue to solve this one. So here given two chemically inequivalent protons. Let's take H and are coupled with the coupling constant 10 Hertz. The chemical shift separation at 500 spectrometer is 5 ppm. So if you look at the spectra, it starts with the 0, right? 0 for this TMS, and we have the delta values. Generally for 1H, we take up to 15 ppm or some most of time in the up to 10 ppm. And we have, let's take one signal here and one signal here. So they are separated by the delta value. This delta is 5 ppm. So they are quite different from one another, right? In terms of the delta values. What nomenclature can be used to represent these coupled spins? So anyone have any idea here? We have two different protons with the delta value. They are quite different from one another. So what kind of spin we use for here? So if you have the
AX.
right. So if you have the two different protons where they are quite largely separated by one another, so obviously it will be a IX16. If they are close to each other in the same, instead of 5 ppm, if there will be a 1 or nearly 1 ppm, right? At that time it will be AB system, inequivalent mention, right? So it will be AB for that. In that case, if the delta separation is 1 ppm at that time. This is given for the benzene molecule, the appropriate nomenclature for the coupled proton of the benzene. So we have in the benzene, we have 6 protons right here, and generally benzene molecule. So all protons are identical here. So for this type of systems, so we generally give A2 here already given. So here A dash, A double dash, triple dash, and in this type of nomenclature we generally refer for this benzene type of systems. Let's take some other example in this one also. And now you should tell the answer. What should be the answer here? So we have here OH, and here we have the nitro group, and here we have the hydrogens. And so what type of nomenclature will be given? So this AA and this HB, they are identical, right? HB, they are identical. This HA, they are identical. So in this type of system, what nomenclature should be here for this one? Anyone? In
A2,
this,
X2.
right. X2 will be the, in this case, if you look at this one, although they are like I mean, two different, like here, this it is like a kind of highly strong donating group, right? And strong withdrawing, but the delta value will not be that much different. So for this one, it will be A2, B2, that kind of, not A2, X2. So if you look at this delta value, it will be nearly 7 ppm, and this will be around 8 to 8.2 to 8.5 ppm. So this kind of system we use refer, I mean, use general the nomenclature A2, B2, that kind of nomenclature. Here, the same example given as we have already solved here, and which is like 1,4 dibromo. So here it is bromo, and another one is 2,3 dichloro, right? So first of all, we just check which these protons are there, and if you look at this proton, they are identical, right? Because it has the plane of symmetry. So these both protons are identical. So for this one, which nomenclature will be the which nomenclature will give for these protons? Yeah, now you got the answer. Definitely, you should be able to solve this one now. So for this one, A2 is the correct answer here for this one. Here, another question is, in the 1000 megahertz spectrometer, the 1H spectra of nitropropane, we have given the nitropropane, right? So it will be, so let's take it is as a N nitro, I mean, there are two different possibilities, right, for nitropropane. Assuming all chemical ships separated from each other by 2 ppm is represented as. So for this one, definitely, if you look at the options A, B, C, three different type of systems are given here for this one, right? So definitely, this first one will be the structure for this one. And in the question, it should be the N-nitropropane. So if I just rub this another text structure, and I'll draw the full structure here. So we have CH3, then it will be a CH2 and CH2 followed by here nitro. So if you look at the delta value, I will just give the approx delta value for this one. So where it will be around 1 to, let's take 1.2. This one, the CH2 attached to the another CH2 which is attached to the electron withdrawing group. So which has the delta value nearly 2.4 or something, or 2.2, and then CH2 attached to the electron withdrawing group. So it is definitely have the very high value. So might be the 3.5 or something. I will just draw the keep the rough value here, right? And we have given what kind of nomenclature will give for this one. So which kind of system this will be? So this is definitely 3 2 2, right? So if you look at this one, in this one, what we will put? Obviously, first will be the A. Now, what will be this one? Which is like quite well separated from 1.22, non-identical as well. And another one is here, which is like group which attached to the highly electron withdrawing group. So which has the value 3.5. So in this one, which kind of nomenclature we can give for this one? So what are the possibility here? So this here, three hydrogens. This definitely will be the A3. Another is the two hydrogen, which is like kind of separated from each other, but not that much, right? So we can write here for the M2, and another is like two hydrogen, which are having the well separated delta values. So for this one, it will be the MX2. So this kind of system we can refer it as a A3M2X2. If you have the same question in the case of any kind of systems, like we have the instead of nitropropane, if you have the butane, nitrobutane, sorry, like this one, in that case, the the similarly, it will be the A2 B2, sorry, A3B2, then we can refer it as a M2 and H2. This kind of systems we can give here. This is just for, I mean, again, because at that time, these two will be the nearly each other, right? So that's why we can refer it as a A2 and sorry, A3B2. But here, they are not that much, in terms of delta value, they are not that much close in this one. So that's why we refer, we put this M2 instead of A3B2. Another question here is the number of allowed transition at chemical site of each spin in the coupled AMX system. We have the system AMX. The number of allowed transition at chemical site of each spin. So does anyone know how to solve this question? We should able to, I mean, solve this question. If you look at the some videos here, this question I will keep as it is for the next uh, next time. Next time I will solve this question. Also, there was one last time also there was one question based on the transition. So the question was, I will just write here. So this was the question was something like this one. The number of possible transition for three non-equivalent protons or three non-equivalent spin. Uh, this was the question, and for that answer was 15. So This question also, I think I have included in the last slide. I will check this question also. Does any know how to solve this question? All right, we'll solve this question later. The next question is the two protons of the dichloromethane are magnetically equivalent protons and pertains an A2 system, A2 spin system. It gives rise to single peaks in 200 megahertz spectrum. The number of peaks detected when the spectrum is obtained on 800 megahertz spectrum here. So we have the DCM here. So we know the structure of the DCM, which has the chlorine, and there will be a hydrogen, another hydrogen, right? So on 200 megahertz, we observe one peak. So the question is, how many peaks we detected in 800 megahertz spectrum for this one? So hope this, I don't think any difficulty for this one, because if there is no any kind of with these both protons are identical, as we have already seen, uh, this Ha and Hb both are equal, right? So definitely they will not couple with each other, right? They are equal, so we will not observe any kind of coupling. So there will be no any coupling, and we observe only one peak. Uh, Whether we take in the 200 megahertz or 800 megahertz, it doesn't matter. So we observe only one peak for this two protons in the 800 megahertz spectrometer. Right. Sure. And we'll take one more question. The last question probably from the assignment. Here we have given two chemically inequivalent protons are coupled. Their chemical shifts are well separated. So we have two protons. Their chemical shifts are well separated. The intensity of two central peaks are equal, and also the intensity of outer peaks are equal. The central peak are 4 times stronger in the intensity than the outer peaks the system uh, pertains to. So this was some question here given in this one. They have given that there are two protons here, and they are chemically inequivalent. Their chemical shifts are well separated. So the chemical shift here well separated. What does it mean? So they haven't given any exact quantity, but in the question it mentioned they are well separated. The intensity of the two central peaks are equal. So let's take the two central peaks. The intensity are equal. Then also intensity of outer two peaks are equal. So I think this one, the central peaks 4 times stronger in intensity than the outer peak. So if I understand the question correctly, so this will be the in the ratio of, let's take like this one. So in this, so like this one, right? 4 times stronger in intensity than the outer peaks. So it means like in the coupling. So what happens sometimes if the coupling get merged with each other. So if the coupling constant are same, at that time what happen? Just because of this first, we observe one signal, and this two also, the intensity of this one will increase. So might be in this manner. So because of the one protons, we get the, let's say, doublet, right? So the first doublet will be in this manner, and another doublet, the splitting due to the another one will be in this manner. But they have mentioned 4 times stronger. I still have doubt here as well. But I think that the key message for this one is the the peak intensity is 4 times. Do we have any kind of splitting which has like 1s2, 4s2, 4s2, 1 this type, this kind of using the Pascal triangle? Any intensity? We have the 1s2, 1, 1s2, 2s2, 1, right? Then also we have the 1s2, 3s2, 3s2, 1. So if you have the core signal, it might have the intensity then 1s2, 3s2, 3s2, 1. So this is definitely due to the merging of peak, right? So it indicate uh, this intensity, the signal we are getting is definitely due to the peak or the signals. They are merged with each other. So definitely they are the uh, closely in terms of the in the NMR sector, they closely lies to each other. So that's why it will be the a kind of similar type of systems which have the similar delta values, almost nearly similar delta values, right? So that's why this kind of merging intensity we are getting in this one. And also, if you point out this the word inequivalent, so definitely they are not a kind of a dash because they are inequivalent. So it definitely the kind of either AB or AX. This is not AB or AX, right? But if we have the AX system, then this kind of the signal merging will not be observed. So this is definitely the AB type system. So in this one, there is not clearly mentioned like where the delta values, but we have given in this one the question itself, the intensity of central two peaks is 4 times. So the central two peaks are 4 times stronger intensity than the outer uh, outer peaks, right? So this one. So if you look at the intensity 1s to 4s to 1, so this will not be the intensity due to the one signal. So definitely it is due to the two signal they merge with each other. So we have sometime what happens, any kind of doublet we have here, and this doublet have the similar delta value. So this kind of merge will happen. So at that time we go observe here intensity 1s2, 2s to 1. So like this way. Similarly in this question, that the intensity this 4 is observed due to the merging of the two signals. Here also in the Pascal angle, if you have the quadrant, this will not show the intensity 1s to 4s to 4s to 1. It should show the intensity in this order 1s to 3s to 3s to 1. So that's why the AB2 is the most appropriate answer for this one. What are the information given from the question? So any doubt in this question? It is not necessarily always you will get in the question all the information. If you look at this question, there are very less information given. So you have to utilize all your uh, other knowledge to solve this one. Here mentioned first key point is inequivalent protons. The another point is the intensity of central two peaks are equal. So we have the two peaks with the equal intensity. Also the intensity of outer two peaks are equal. So the outer two peaks are also have equal intensity, whatever it is. Then again, it is mentioned the two peaks are four times stronger. So this is as a 4:4 than the outer two peaks, right? So the intensity in this form for the signal right here. So that's why we came up to the answer. This will be the AB2, and we have neglected this two because it is chemically inequivalent. We have neglected AX system because if it is AX, then this type of merge will not be the observed in this one. And the two options remain A dash and AB. In this one, they are the inequivalent, so we can neglect this one also here. So here the AB is the most appropriate answer for this one. Any doubt here? I will just take the last question that in the last time that we have uh, not solved. So here, are you able to see my screen? This was the question that last time I told someone has asked, right? And I told I will solve this one in the next video. So here we have given the question: maximum number of transition expected in the 1H spectrum of the three coupled spin. So here uh, yeah, here also answer 15 was the correct option because if because of this one uncoupled one, we'll get the one signal, the first signal here. After first splitting, we get the second and the third signal, and then fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, 13, 14, and the 15. So we get the 15 answer here because of these three coupled spins, irrespective whether they are strongly coupled or non-coupled. So these are the 15 possible transition expected for the in the NHL 1H NMR of the three coupled spins. So the 15 was the correct answer for this one. Also, we have the same question we have solved here today also. We have seen today there was one question. Yeah, this question. Uh, this question is from the selection rule. So I don't have the exact formula to calculate this one, but I think from which video it is, I still not remember. S- But I think you should look this one in the video. You will get the answer for this one. So any doubt except this question? All right, if you don't have doubt, we'll stop here for today and we'll see in the next on the next Tuesday. See ya.